Awesome. Hi, everyone. Welcome to this week's Friday presentations. This week I'm going to be talking about something pretty interesting. It's called DHyper, a recurrent dual hypergraph neural network for event prediction in temporal knowledge graphs. I promise you, it's not as bad as it sounds. We're going to break it down today in really simple terms and learn about some new things. My name is Griffin Higgins, and my supervisors for this directed studies course are Prof. Ali Grobani and Dr. Chen. A little bit of introduction. My name is Griffin Higgins. I'm a PhD student in computer science here at UNB. I'm also a cybersecurity software developer here at CIC. And for this week's nerdy things, I'm actually starting to run out of nerdy things about myself, believe it or not. There's an interesting game that's coming out, I think next week. It's called Forefront. It's kind of like Call of Duty, but it's in VR, so you get to fly helicopters and all that kind of stuff. So yeah, I'll try and balance out that in between reading my papers. For an introduction, or for the overview, I'm just going to cover our paper, and then I'll break down my critical review and personal review. We're going to cover the methodology, experiments, results, you name it. So just getting into it, we often want to understand relations between things, right? And this is often very informative for us. But something else we're often interested in are information about relations among things or among groups. So very simply, I always talk about graphs, and we might recognize this where we have nodes and edges between nodes where we can only have two nodes for one edge, right? But this week we're going to talk about something very interesting, and it's known as a hypergraph. So believe it or not, we can actually generalize graphs even further beyond what they already are. So normally, as in the previous slide, we see that there's only two nodes between one edge. But what happens if an edge can actually connect multiple nodes? This is kind of strange to think about. It's not something we often do. So that's something we're going to talk about today. And we often denote this in something called an incidence matrix, as opposed to an adjacency matrix that we're all familiar with, where we might have the nodes as both columns and rows. Here we're going to have the nodes just as rows and the edges themselves as columns. So this is going to be kind of interesting. But this is kind of strange to think about, again, like a multi-edge graph thing. What's an easier way to think about this? Well, we can think about them kind of as blobs, as connected blobs. So we can see that this is still going to connect up those two nodes, presumably by like an edge. But we might also consider a group of nodes together, and that would be a hyperedge. So we can think about them conversely. But as abstract as this is, where might this come up in the real world? Well, this might come up if we're trying to model countries, for example. We might recognize that there might be members of like the G7. So even though maybe there might be relations between Canada and the States, we might be able to draw a literal edge between those two countries. We might consider a wider group of countries together that we might represent with this kind of hyperedge. So that's one thing we're going to use today. Another one is a knowledge graph. So we're going to tack on a temporal dimension too. A knowledge graph consists of a head entity, which we might denote here with New Zealand, as well as a tail entity that we might denote with here as Greece. We might also specify a relation or something that's actually mapping these two things together. So for example, we might say that these countries are going to express intent to cooperate. And then the last thing is that we might change this kind of knowledge through time. So this might be occurring in 2018, for example. So that's a little bit on a temporal knowledge graph. And next we're going to move into event prediction. We're just going to cover all the very small subtopic Lego pieces before we put them all together in a moment. In event prediction, it sounds exactly like what it is. If we have a series of events occurring through some kind of time step, we might unpack one of the events as a temporal edge that we just discussed. So we might say this is going to be an event for us. But we might also be interested in trying to predict future events. So given all these events in the past, there's some kind of new event that might be happening between two countries, maybe New Zealand and Greece. In 2018, they were expressing intent to cooperate. Maybe in 2020, they're going to not be cooperating, or some kind of prediction based on a lot of things that might be happening in terms of the events preceding it. So that's a little bit on event prediction. We're going to talk very briefly about graph neural networks. I showed a quick video last week on graph neural networks, so I'm not going to do it again this week. But essentially, the main idea here is that we can represent each node by its neighborhood. We can even think about like departments in a university. So all of us, we might be a very unique neighborhood as opposed to maybe the NBIRDT that has a lot of different people that work inside of it. And if I were able to describe someone here, we might describe CIC by all the people that work here. So that's kind of how a neighborhood might be represented in one of these nodes. And presumably, if we aggregate all of these neighborhoods together, we might have a very unique representation for the graph, or maybe for UMB once all of these organizations are aggregated together. So we can kind of see what that unique representation or that neighborhood might look like for each kind of node, and we can understand that it might compose multiple layers of references. So that's where that uniqueness is going to be derived from for a particular node. Great. We might also consider different kind of tasks. I've done a lot of work in the graph classification kind of area of tasks, where we might be trying to say, hey, given a piece of code represented as a graph, is it malicious or is it benign? But we might also be interested in node level tasks, i.e. trying to classify what a node is, or edge level tasks that we're interested in today. So deciding if there is an edge or if there isn't an edge, or even kind of a classification task on an edge. So maybe countries are trying to cooperate, but maybe they're trying to do something else, and predicting what that edge is going to be our main task. So that's great. We just covered a lot of different things. We covered hypergraphs, we covered temporal knowledge graphs, we just covered event prediction and graph neural networks. So give yourself a little pat on the back. You're doing very well. We're covering lots of different topics. So coming to the work that we're going to be talking about today, we're going to bring all of these things together in the following form. So here, this is the overall architecture methodology for what the authors propose, and we're going to break it down in little chunks before we keep going on. So the first thing we're going to do is we're going to consider an entity graph. So just spoiler alert, the data set we're going to be using is with countries, and we're going to be trying to predict future relations between these countries through time. So we might think of the entities themselves as countries, and here we might be trying to figure out those groups where we represent the group of these countries together as a hyperedge. So this isn't like a typical graph that we're used to thinking about, it's a little bit different. So that's the first thing we're going to do. We're going to take this entity graph, we're going to transform it into an entity hypergraph. How we do that, we'll talk about that in a moment. We're also going to take our same entity graph and we're going to construct something called a relation graph. So here, this is basically tricky to think about, but it's the neighborhood of edges around a given edge that we are going to now represent as nodes. So for example, if we consider this edge R4, we can understand that it's going to be in the neighborhood of R5, R2, and R1. So if we look, you can see R5, R2, and R1. There's like those kind of three connections. So that's how it's going to move from one graph to the other. After this is kind of a two-parter. We're going to take this relation graph and we're also going to transform it into a relation hypergraph. So here again, we're going to consider groups of relations together. So this might be kind of a cooperative set of relations, or it might be some other kind of set of relations. Importantly, there might be higher order relations. So we just talked about one, it might be like a conflict, for example. It might be a prior meta kind of classification, or we might understand like maybe like a small arms conflict, or maybe a naval battle, or something like that would be part of this wider classification as a relation. So I kind of skipped over how we actually transfer these things into hypergraphs, but effectively there's going to be an optimization that's performed where we take the entity graph and we transform it into the entity hypergraph through a multi-layer perceptron. And this is interesting because we employ two things. We employ something called sparse max, and we also employ something called low rank matrix factorization, which is kind of like singular value decomposition, if you're familiar with that. Also, in sparse max, it's not like softmax where we're only trying to predict one kind of outcome. Mahdi also just talked a minute ago, we might have like cats, dogs, and birds, and we're just trying to predict, like I give you a sample, tell me which one it is. But here I might be saying like, here's an edge, what are all the entities that might belong to that hyperedge? So it's kind of a multi-label classification, or multi-label attribution problem. After this, after we transform all the graphs into the hypergraphs, We're then going to take them, and then we're going to perform message passing on them through just a standard GNN. There might be some interesting things that happen on the hyper edges, but we can still pass messages around. Formally, that's defined through the following. So the first stage here, the entity to hyperedge aggregation and the relation to hyperedge aggregation occurs first, and it occurs through the following formula. So again, we're just going to sum up through all the entities, and that will be representative of this, this first part of the graph. The next part is we're going to also sum the neighborhoods of these things together. If we have questions about this, I can come back to it later, but I just also want to be mindful of time. And then afterwards, we're going to take the relation. Just need to take a quick peek so I can see it. We're going to take the relation to the entity user. We're going to take the relation to the entities, and we're also going to fuse that that embedding with the entity to relation, and we're going to fuse those as well. So our final graph is going to know about a lot of different things. It's going to know about the different relations that the entities have amongst each other. It's going to know about the relations that the entities have amongst each other in terms of the groups that they belong to, and the same two things are going to hold for the relations. And then we're going to fuse all of that information into one compact thing so that we might be able to later predict some more stuff. So this is actually just one part of a wider module. I mentioned earlier that this is working on temporal knowledge graphs. So we're going to basically package up everything we just talked about into the following little box, and we're going to consider it as such. We're going to take this box and we're going to place it into its wider context, where we're going to start with the following entities as well as their relations, and we're going to pass them through kind of like a sequence model, where at a certain time step we might have so many entities and relations that have occurred. So maybe Canada and the US are trading 1 minute, and then at another time step we might be doing something else, and the graph might evolve and change over time. So we'll take this first embedding, and we'll pass it to something called the attentive temporal encoder, which we'll go over in a moment. And we'll take this representation that's output from our dual hypergraph neural network, and we're going to pass it through a residual gate. And this is basically going to control how much information will actually flow forward into the future so that we can make better predictions. Again, here's some more formalisms just for what's actually happening on the residual gate, where we're just kind of taking the dot products between lots of like multi-layer perceptrons with different kind of weights that figure it out. But again, we're just controlling how much information kind of seeps forward from the past into the future. More specifically also for the attentive temporal encoder, we can see that it's going to employ something similar to a transformer, where we might consider the positional encodings. If you've ever looked at the transformer positional encodings, you'll see that they do lots of unique things with cosine and sine waves. Essentially, that will just be kind of a unique representation for whatever that position will be across time, so that's why we use it here. As well as this is more or less just the attention in this block that's given to each part of the output from the following models that consider the previous time steps as well. The authors use the following model. They use convfc. So basically this is a convolution operator, because they're going to look at each kind of chunk that's output in order to make predictions about what will happen in the future. So in terms of the experimental setup, again, they use the same architecture, and they also use cross entropy loss across all the training samples and over all the different relations. So that kind of takes the following form, and I know Matt D also covered that just a moment ago, so that's great. In terms of hyperparameters, the authors use something pretty interesting. It's called tree structured partisan estimators. Essentially, this is a Bayesian optimization in order to search through different hyperparameter configurations for a model. Essentially, this is just like smart grid search, if you want to have it in the simplest terms, where if we have different hyperparameters for a model, for example, if we're working with multi-layer perceptron, we might control the number of neurons and the number of layers. This will just search through this in an effective way instead of just grid searching through the whole thing. These are kind of some of the hyperparameters they test out. And this is important too, I forgot to mention this earlier. the number of hyperedges that might exist amongst the entities as well as amongst the relations is a hyperparameter. So that's not just something that the model can go figure out, that's something that we have to define right up front. We also consider a set number of layers for the message passing, and we also consider hyperparameters for the length of the historical window, so we can see how many time steps into the past are being considered in order to predict things in the future. The authors use batch size of 16 and hidden representations of 100, and they use 200 in the residual gate. They also use Atom with a learning rate of 0.01. In terms of the data sets, they use the integrated crisis warning system as well as the global data set of event, language, and tone. We can see that some of the training and validation sets have over 1 million samples, so that's wonderful. And we can see that the time granularity is changing a little bit for each of the data sets. Some of them consider them in terms of 24 hours, some of them concern in 15-minute increments, so we can see how fast things might be changing in those instances. In terms of metrics, they use the number of hits at a given K. So these are pretty interesting. I haven't come across these before, but essentially we're trying to figure out the model is going to predict a set of relations in a top K amount of things that might happen, and we're trying to see how many of those might be right for a given top K. We might also look at the average reciprocal rank of the relations themselves. So essentially here we're trying to figure out when we make a prediction about a given relation between two entities, how accurate is that in terms of where it comes up as its first rank. In terms of baseline, they look at lots of different types of architectures. They look at shallow encoder-based approaches, they look at deep neural network-based approaches, and they look at derived structure-based approaches as well, so lots of variety there, which is great. In terms of the evaluation, they don't have any exciting plots and stuff, just lots of tables here, sorry. But the results are very clear. The dual hypergraph neural network model performs the best in every case across every data set, so that's great. And we can see that there's improvement gains of 17% or even 30% in some cases, so that's really good to see. And again, this is just through the different data sets. Nothing too noticeable, again, other than just that it's performing the best out of all the different approaches. The last thing that they consider is the entity prediction task. Forgot to mention that all the previous things we just looked at a moment ago, where this model achieves state of the art, this is on the relation prediction task. So again, between two countries, are they going to cooperate? Are they not going to cooperate? But now we're trying to look at the entity prediction task. So I give you a country and I give you a kind of relation, and now we have to figure out what the other country might be. So that's kind of another prediction task we might do, where again it achieves the best results across all categories. Here, in terms of the evaluation, they also look at varying the number of entity hyperedges as well as the number of relation hyperedges. So how many groups we're allowing in each of these kind of time steps. We can see here that as we increase the number of entity hyperedges, that the results kind of increase up to a certain point. And as we do the same for the number of relation-based hyperedges, they'll start to decrease after a certain point. So finding that optimal number of hyperedges is important. We can also vary the length of the historical window. So if we only look back one time step for whatever that time step would be for that specific data set, i.e. some of the data sets go back by 15 minutes, by 15-minute increments, some of them go back by 24-hour increments. So that's kind of saying what is a time step in that sense. We can see that again, they start to increase up to a certain point and then they drop off. So finding that's important. And then the number of layers in the message passing neural network, around 2 to 3 is kind of standard. That's usually what you see. After that, you get a problem where the messages kind of converge. So that's not good. But yeah, two layers is great. Here they also do something pretty interesting. They look at the visualizations of the entity representations. So we're basically saying if we have this prediction right before we make the prediction, and we look at where all the entities are in this very high dimensional space, if we instead collapse that into a very low dimensional space that we might understand, where are all of these entities? And again, just in simpler terms, this might be like if you're playing Call of Duty, you can see your character kind of at the center of the 3D screen, you can see the whole world around you. But if if you look at the mini map, you'll see this kind of like 2D representation of the world. That's kind of like what we're doing here, just in much higher dimensions. So I'm also going to blow it up a little bit so we can see. But we can see here in this other model that they consider Evo Explore, the representations are kind of clustered pretty densely. But in our DHyper model, they're kind of pushed out a little bit more, and all the entities in like the G7 are also here. So that's really interesting to see that the model has picked up on this hyper edge, or this group between the countries or the relations or the entities. We can also do the same thing for the relation representations, and again, we're going to blow it up a little bit. So here we can see that some of the different relations that might say use conventional military force, or provide military aid, or criticize or denounce, all these things are quite far from one another. But then in this Evo Explore model, but then in our DHyper model, all of these things kind of become a little bit closer together as it relates perhaps to its hyper edge. So that's interesting to see as well. And again, this isn't like the end-all be-all proof. We are taking very high-dimensional things and we're collapsing them down into a very low-dimensional space. So it's also possible that depending on how we've seeded our TSNE models, the model we use to do the dimensionality reduction, that it might be a little bit different. But it's good just to take a look. That's great. After this, we also can look at a real kind of test case for how this might perform in the wild. So, or not in the wild, but just in terms of real data. So if we have the following, if we have Russia and then we have Ukraine, these will be our entities. And in 2014, we might try and say, like, what is the relation between these things given all the prior data? So we might see that this model, the TIRGN model, says the top thing is going to be engaged in diplomatic cooperation, maybe not. We might see the Evo Explore model will suggest host a visit, and then our DHyper model says criticize or denounce. But it also makes lots of other correct predictions in the top K. So that's great to see that our model is doing much better than these other models where this gets 1, 2, 3, 4, 5, 6 right. This one gets 3, that one gets 2. So that's great to see that our model is doing better. In terms of the ablation, this is a very complicated ablation, but they take a look at a lot of different things as they pertain to our architecture, which we just saw was quite complex. I'm not going to cover all of them. The main message is just that all of them are necessary in order to give our DHyper model the performance that it has. If we have questions about that, please feel free to ask. We can also do the same for the relation, this ablation is for the first part where we're making the hypergraphs. This ablation is for the second part where we're doing like the message passing and things like that, and as well as the attention module. In terms of the conclusion, the work considers relations among entities in temporal knowledge graphs. The authors propose DHyper to capture such information, and it achieves a state-of-the-art on 6 real-world data sets for event prediction. In terms of my critical review, I'm just going to kind of jog through this quickly. I would say complexity analysis is included. That's one thing that's really good in the work, but it's nice to have it be comparable with other works. I know how tricky it is to dig through and reverse engineer all these complicated machine learning models to get their big O. So even if the authors or someone else wants to just give empirical, just kind of average time bounds on maybe some small task, that would be enough just to compare. Some questions I would have would be like, what about the time frames with extreme graph sizes? Maybe there's some time step where lots of entities suddenly arrive and there's suddenly lots of relations, or maybe there's none at all. What do we do in those kind of scenarios? And then what about binning the time by months instead of by days, so you get kind of a wider view on what the relations might have been up to a certain point. Some other critical review things. It took me a while to dig through. The authors who changed their GitHub from this XT23 to the Diamond 159. That was just on their GitHub, and I saw the user was in the other GitHub page, so they should change that. Something I would say is I'm not fully convinced that the tree pars and estimators give the best hyperparameters. Generally, if you use like these kind of Bayesian optimizations, they'll give you good hyperparameter settings, but there's no guarantee that they will in fact give you the best. So if people just want to say best estimated hyperparameters, it's a little bit of a nit, but it's important. I'm going to skip over my personal review. I thought it was great, so we can maybe come back to this. Here's some of my references, and thank you so much for listening. I hope you enjoyed learning about hypergraphs and all these interesting things.